In this video, we will solve the following problem. A mass M2 is suspended under a table by a string, which will go through a hole in the table and is connected to a second mass, M1. The second mass M1 slides frictionlessly along the table and undergoes uniform circular motion. The problem asks us to find what the speed of that uniform circular motion is for mass M1. So it asks us to find v. Now the idea for this problem is to use Newton's second law and uniform circular motion. As with any Newton's second law problem, we need to start out by drawing a free body diagram. We have two masses in this problem, mass M1 and M2, so we need to draw a free body diagram for both. We will start out by drawing a free body diagram for the mass 1. There are three forces that I can recognize on the body mass 1. Downward, we'll have a force due to gravity. Upward, we will have a normal force that prevents the mass from going through the table. And towards the left, we will have a force due to tension from the rope that is connected to object mass 1. The free body diagram for mass M2 is as follows. Let's take a look. M2 is hanging suspended under the table. As can be seen here, it will only have two forces that I can recognize. One of them will be the force due to gravity, and the other one will be the force due to tension. After we have drawn the free body diagram, we need to write out the equations associated with each of these objects. The equation for us is Newton's second law, which has the form the sum of all forces is equal to mass times the acceleration. Now this is a vector equation, so we need to break this into components. I'm going to define my components as such. I'm going to have x towards the right. I'm going to have y up the page. The x component for mass 1 is going to give us the following. We have only in the negative x direction the force due to tension. This should be the mass M1 times the acceleration in the x direction. In the y component, we are going to have in the positive direction the normal force, and in the negative direction the force due to gravity. This will be times M1 times the acceleration in the y direction. But M1 is not moving or accelerating in the y direction. It is stationary. It is not moving through the surface, so we can set that to 0. For the second object, we only have a y direction, so we don't need to bother with the x direction. Writing that down, in the y direction we have positive a force due to tension minus a force due to gravity is equal to the mass M2 times the acceleration. But again, the acceleration for that suspended mass should be 0. It is not going anywhere, and more specifically, it's not accelerating. At this point in the problem, we have written down all the equations that we can from the physics that describe the problem, and we need to try and solve the problem. What we have not used yet is the idea of uniform circular motion. We have mentioned that in the x direction we have the force due to tension will cause some acceleration in the x direction, but we can identify that, and we can say that the acceleration in the x direction must be negative v squared over L, where L is the radius of the string, the length of the string above the table, and is going to be the radius of the circle traced out by M1. V is what we are looking for, so we can substitute that into the equation as we see. Plugging this in to the x, we get that minus the force due to tension is equal to the mass M1 times negative v squared over L. At this point, we can use the y equation for the mass M2 to solve for tension as well. This gives us that the force due to tension is going to be replacing the force due to gravity for m2 with the formula m2 times g, the acceleration due to gravity. Substituting that in to the other equation that we have already, this gives us m2 times g is equal to m1 times velocity squared over L. Now, solving for velocity, we get this is m2 over m1 times gravity times L, whole thing under a square root sign. That is the solution to the problem as it has been asked, which is, what is the speed necessary for that uniform circular motion such that m2 is suspended under the table?